Hey, it's me, Destin. Welcome back to Smarter Every Day 2. Today, we're going to talk about film, and this is Ektachrome, and this is Ektar. These are both made at the Kodak film plant in Rochester, New York. Today, we're going to talk to a world expert in film chemistry, Dr. Jeffrey Hansen, and Jeff is amazing. He's very kind, he's a fantastic teacher, and you'll see as we have this very in-depth discussion about the chemistry of film, he is an excellent teacher. He has the ability to take you right up to the edge of what you're capable of understanding, showing you that there's stuff beyond that, but then backing it off and just keeping it right there so that you can just grasp it for yourself. So I love this interview. So what you're going to see here is Dr. Hansen shows me how film works. He's explaining all the things that I can't find on the internet. If you've ever tried to understand film chemistry, there is not a good resource on the internet. So I wanted all this to live on the internet in this form because it's straight from the horse's mouth. Dr. Hansen understands it all. A couple things I want you to look for. We're actually going to see like where they make the chemicals in the Kodak plant. It's right before the weekend, so there's no workers inside doing the chemical stuff. It's like you get to see the kettles where they make it's amazing. So I hope you enjoy that. But also another thing to keep an eye out for, or keep your ear out for, is that some of the things that they're able to do with film, you can't do with digital sensors. Like you can send messages up and down different layers, and I find that to be fascinating. So anyway, I wanted this video to exist. I'm glad you're sitting here and you're about to watch it because it's amazing. Please enjoy Dr. Jeffrey Hansen at Kodak in Rochester, New York. I want to know how it works, and I know it has something to do with something called silver halide or silver halide.
Both are good.
Both are good?
You'll probably hear halide out of my mouth.
Okay.
All right.
So teach me, Jeff. How does this stuff work?
So what's silver halide? All right. So silver halide is nothing more than a crystal structure of two materials, silver and a halide. Might be chloride, might be bromide, could be iodide.
And what is a halide?
So a halide is the group 7 elements on the far right of the periodic, not far right because those are the noble ones, but one back.
Okay.
All right? But this is an ionic crystal. So imagine the red is silver, the green is halide, and this is a cubic rock salt structure material.
Okay, I'm seeing a gap on this side. Is that supposed to be there?
So you're seeing a cut?
Yes.
Well, because I'm going to talk to you about interesting things about structures, maybe.
Okay.
The other one is this one, which is pretty, the one here that you got all green, that's a very important surface. That's the top surface of the tabular grains.
I'm seeing a triangle here?
Yep.
Okay.
You're seeing all one ion.
Okay.
All right, and you can see planes of those as you go down.
Okay, planes of just green. Okay.
Green, red. Depends how you tilted it, you'll see it.
Okay, I see it. There are planes of green. What is the green?
So in this case, pick it, we'll call it halide.
Okay.
And the red is silver.
Okay.
But the point is this is nothing more than sodium chloride structure, but silver halide has a very interesting phenomena. Those ions of silver that are in these neat lattice sites, they move.
Okay.
They're mobile.
Okay.
And it's because of that phenomena that photography works.
Okay.
Mobile interstitial silver ions is why photography works.
Okay.
All right. So you got to find a way to make this stuff, all right? And we use precipitation. If I can bring in a jet of silver nitrate and a jet of, let's say, sodium bromide, I will get silver and bromide to react together and begin nucleating small little crystals that will eventually grow.
Nucleating meaning they solidify?
Yes, yes.
Okay.
So we get to a supersaturation condition where they no longer will stay in solution. We've got too much in solution, and it begins the process of crashing out.
Okay.
Okay? If you, I'm trying to think of a good example of precipitation at home.
Oh, I've seen it. It's like those little hand warmers when you click the button and it'll grow the sodium hydroxide or whatever it is.
Yes, maybe.
Okay.
All right. But we precipitate microcrystals.
Okay, so you grow silver halide or silver halide.
And under the right conditions, and in the presence of gelatin, which is our peptizer that helps support the grains and keeps them from interacting, water, gelatin, silver, and halide allows us to begin the precipitation process.
Now, when you said a peptizer, which is a word I don't know, does that mean like something that holds the grains apart from each other?
Let's pretend that that this picture is that situation. But in a cross section like this, here's one we'll talk about eventually.
It's three-dimensional.
Yep. But all the stuff inside here, between the black lines and stuff like that, that's the gelatin.
Okay. So it's a matrix. Got it.
Yep.
Got it. So we're dealing with a composite where we have a matrix of the gelatin, and the aggregate in between would be the silver halide.
Right. And so this is before it's ever coated. So we're not even thinking about this.
Okay.
Literally, I'm thinking about a kettle.
Okay.
And there's a kettle picture on the wall, which we'll go up to and see.
Okay.
All right. And we'll be up close and personal. The big, probably, like I said yesterday, Kodak, probably our two big core competencies are the precipitation of these and coating.
Okay.
All right. For Kodak, we make 127 different kinds of silver halide.
Okay.
All right. And it's everything from size, 50 nanometers, 500 angstroms, 0.5 microns, very tiny, all the way up to maybe 3 microns.
Okay, so I'm starting to understand, because in film photography, the more sensitive, this is 800 ISO film, the more sensitive my film is, the more grainy the photography looks. So that tells me that the larger the crystal of silver halide, the more sensitive it is to light.
Big capture area.
Oh, okay. So
So imagine a crystal like this being in a film, facing up. This would be now a layer.
Okay.
The light comes down from the top of the film, and the bigger the grain is, the more likely it'll start developing.
Got it.
So fast emulsions and slow emulsions.
Okay. And so the way it starts actually to change is a photon hits it, and what does it do to the grain structure?
Very good. All right. So a photon creates a electron and a hole. So the photon hits the surface and creates this pair.
Okay.
If the hole and electron go back together, they annihilate each other, and it's as if it never hit it with light.
Okay, I'm not even going to pretend like I understood what you just said. So you said a photon. So this is our crystal.
Yep.
So a photon. Can you? Here it comes.
Yeah. I mean, imagine at the top of this is something that catches photons, and we'll talk about it in a little bit.
Okay.
But this whole crystal could absorb that photon.
Okay.
Silver halide, before we put up special chemicals on it, is only sensitive to ultraviolet and very short blue light.
Okay.
So without some dyes and stuff, you could only take UV pictures.
Got it.
But a photon comes in, it gets absorbed. And if I talked solid state physics, I might lose you a little bit more, but it's the issue is it gets absorbed, and you create a hole, a positive part of the photon after it's been annihilated.
Okay.
And a mobile electron. And the electron is important because it can then bump into, get trapped, and we'll talk about that a little bit, with the silver ion to create the first silver metal atom.
Okay.
So our goal is to make a stable silver atom cluster that can make it all the way through to photoprocessing.
Okay.
But until they're big enough cluster, they're kind of ethereal. They're not going to last very long. So our goal is to make sensitivity centers that can collect those silver atoms to, and we tend to say between 3 and 5 silver atoms for a developable center.
Okay. Got
All
it.
right?
Yeah. So so you have these. Are these developed?
So these are actually the crystals. They're not developed. This would be as it is before it's ever coated.
Okay.
And we would characterize them on their shape, their size, the different faces that you see cubic faces.
So you have a scanning electron microscope that you're looking at this stuff with.
These are all SEMs, scanning electron microscopes.
Okay.
Optical microscopes, these would be way too small. You can see these, but this is all electron microscopes.
Got it.
Yep.
Okay.
All right. So precipitation is pretty important to control the parameters temperature, mixing speed, the composition of the solution that they're precipitating. We'll talk a little bit about that when we're upstairs. But this is our mixer. And you can see how heavy it is. But,
Yeah.
the interesting thing is we call this the planar emulsion precipitation apparatus. PEPA.
What's it called?
PEPA.
PEPA.
And the issue is when you're mixing, you also need to pump things around the kettle.
Okay.
This does both. So we bring in with
It's like two pumps that crash into each other.
It's a way to put it, yeah. There's a pump from below. Comes in these holes.
Yeah.
Shoots out, and then we'll shoot
Yep.
out horizontally as this thing spins.
Okay.
So these will suck in. Where's the? Oh, here it is. All these little holes here is where the silver from the top side, or the salt from the bottom side, will come in to these holes, and the residence times of those ions is an important part of the controlling the precipitation.
The size of it.
The nuclei that we make.
Okay.
So imagine this makes millions and millions of nuclei, and at that point you say, well, I want to make cubes today, or I want to make tea grains today.
Oh, really? So you're not only controlling the size and the quantity, but you're controlling the shape.
Absolutely.
So this is the wizardry part.
This is definitely the wizardry part, because it's years and years of learning what factors control them.
Wow.
Because at that point, we actually begin the process of saying, we're making a big grain today or small. If it's small, we're going to have lots of nuclei. If it's big, you could imagine only having one where everything grows on it and it's monstrously large.
Right.
So the control of the kettle conditions, pH particularly, and we'll talk a little bit about that, we digest those nuclei to get to the number we want.
Okay.
All right. After that, the choice is, what grains are you going to make?
Okay.
That's just the base structure of the grains. Now we put internal things into it, like dopants, metal atoms that go inside that help the photographic process. Ruthenium and iridium are key materials.
Did you catch all that, Trent?
I'm just like,
I told you.
Yeah, it's legit.
I told you I was going to talk about it. all
Okay,
right?
let's bring it.
If you want me to twist around and go
No,
away,
Jeff, keep
all right,
going.
all right.
Just I want to receive the information.
The point is metal dopants control the time scale of the photoelectron.
Ruthenium and
Iridium.
iridium. Got it.
There are other ones we've tried.
Those are
but
precious.
They are precious.
Yeah.
You know, iridium comes from?
I don't know. It's atomic number 60.
Oh, I don't know. I can't even remember that.
Yeah.
So the source of it comes from cosmological events.
Really?
Yeah. You know, asteroids hitting the Earth.
Wow.
So they're found in, you know, nice sheets in areas because they get exploded around. So it's very rare material, but available.
Okay.
And it helps control the electron lifetime. And I want to talk a little bit about that. So remember I told you about a hole and an electron?
Right.
So that if they actually find each other again, it's kind of like what was the Star Trek story? You know, the good side, the bad side, they come together and destroy them. So Lazarus. All right. I know. No, I'm geeking out. But the hole and the electron get together and they annihilate each other.
Got it.
It's as if the photon never hit the grain.
Okay.
What we want to do is make sure those things kind of separate in space and time so that the electron can be released at another time when there are other electrons around.
Okay.
Iridium helps you do what's called a ruthenium helps you do a shallow trap.
Okay.
Where the electron's protected.
Okay.
All right? Okay.
I got all that.
All right.
Yeah.
At that point, I'm going to take you to chemical sensitization.
Okay.
So all I've done now is make silver halide crystals that can absorb light, but it would be part of black and white photography where you only look at ultraviolet or blue light.
Right. So we have to make it so that my guess is we're going to put some chemical right beside it it is sensitive to visible light and it kicks off ultraviolet. Is that what you do?
If you left off the kickoff ultraviolet, you'd be great.
Okay.
All right. So let's look at another cross section, okay?
Okay.
So here's an example of what we were watching yesterday coat.
Okay.
All right. This is a multi-layer film.
Okay.
Where at the bottom we have cyan imaging emulsions.
And these are different sensitivities of cyan.
Yeah, think of the fast, the mid, and the slow as being the biggest, the middle, and the littlest.
Got it.
And cyan-sensitive emulsions are going to absorb red light.
Okay.
All right? So, you know, when we think about a negative image, there's a cyan that's sensitive to red light, there's a magenta that is sensitive to green light, and there's yellow that's sensitive to blue light.
Okay.
And we create those in this kind of pack.
Okay.
Between the cyan and the magenta is an inner layer where we put chemistry to avoid the light going from one layer to another. So I don't want any green or, well, particularly green light going down to the red layer.
So these are filters. These inner layers are filters.
Absorber dyes, yes.
Absorber dyes, okay.
Okay, and then as you come up the pack, the magenta layer is sensitive to the green light. And the important part, what I told you about ultraviolet and blue, all greens are sensitive to that. So we definitely have to stop blue light from going to the bottom of the pack. So underneath the yellow layer, we put a yellow filter layer that stops all blue light from going down.
Okay.
And then we top off with yellow. That gets you the ability to absorb all the spectra. From blue to red.
So one question, if I've got crystals in here of silver halide,
Yep.
then I would think that I would be obscuring the layers before just because the light has to physically get by the crystals.
Absolutely great question.
Okay.
Right? Yes. The difference is that on these T-grain, tabular grain crystals,
That's the
big triangle looking ones.
It's like a tetrahedron kind of thing.
Right, but the difference is this might be 2 or 3 microns across, 0.1 micron thick.
Got it.
So it's like a piece of paper or a plate where there's a top surface and a bottom surface. And we put down a single monolayer of dye on the top and the bottom. And they can absorb light. At that level, yes, there's some shadowing of the light going lower, but you know, only if you start building up really thick amounts of these dyes will it completely block. So it's actually a wonderful feature of film to allow light to go through the top crystal and go down lower.
Literally through it. So
absolutely through it.
It can shine through that crystal.
Yep.
Okay.
Not all photons are going to be absorbed by the dye.
Got it.
So that's a completely different thing than a digital camera.
Yeah, a digital camera, you have a presented area with a Bayer filter on it, and the photons have to hit and it has to respond, and you're filtering RGB based on the position in the Bayer filter.
Exactly. So we kind of have what we call multi-layer detection.
Oh, okay.
All right, all those different layers can detect the photons coming through. Because we use 3 colors to cover the spectra, that's where photography is different than your human eye.
Right.
We will have parts of the dye that overlap each other, and that will cause unwanted imaging. So we actually put in chemicals to control that.
Okay.
But just so you know that right now we've created 3 color records to cover the visible spectra.
Got it. Not unlike well, it's kind of similar to our eye that has, except our rods and cones. Our cones are RGB, mostly G.
Right.
Right? Okay. I'm with you. I'm hanging.
You got it exactly right.
Okay.
So your eye's continuous, and we have, you know, kind of digitized color areas.
With silver halide. So we have bands that we can absorb.
Yes.
Different wavelength bands.
And that's called the ability for us to do color separation.
Okay.
Which is why, where's my guy? There he is. That's why when you take a picture, you see those 3 records.
Okay. Got it. So I've seen film stock that is more magenta or more blue, and that's because the amount of dyes were off. Maybe on purpose.
So there are ways you can do that by putting filters in front of the lens.
Oh, okay.
Okay. So we try to make it so that the film is a neutral balance.
Got it. And
so
do you
not
usually,
one color more than another, but it can happen, yeah.
So you control the color balance of the film by how much of each silver halide crystals you put in each layer.
Yes, kind of. When we talk color balance, our most important thing is where's your light source, all right? So you'll see daylight balanced films and tungsten balanced films. Why is that? Because a tungsten balanced film doesn't have much blue light.
Okay.
Very sort of. So in motion picture, where they're definitely tungsten balanced, our fastest record is the blue record because it's got the least amount of light.
Got it. So it's adjusting.
Yes. Well, adjusting. We are trying to create a neutral exposure when we know that the light hitting the subjects is not balanced.
You're tipping the scales.
Yes, I'm definitely tipping the scales.
Got it.
Okay?
Okay.
That's a good way to put it. I'm going to use that.
Yeah, it's yours. You want it.
All right, so we've been talking a little bit about the crystals, the light that's coming in. Now I got to talk a little bit about the other chemistries, all right? So we talked a little bit about the 3 atoms to 5 atoms of silver. And one way to improve the performance is to use other chemicals, gold and sulfur.
Really?
To stabilize those latent images, to create sensitivity centers where the silver says, hey, I want to go there.
Okay.
If I pre-prepare a gold sulfur aggregate of molecules, silver might like to go there.
Okay.
And one of the things when we've got this big T grain is you don't want to have a million all over the place because they might be too small and not develop. We want some that are preferentially.
So you want all the silver to aggregate to one side.
It would be great.
And start growing in one location.
We would love to have a working single sensitivity center that doesn't decay. And we actually like multiples for different reasons. We'll talk about it. But
sure.
We don't want a million of them because that'll actually create a reciprocity failure. And we'll talk a little bit about that maybe.
Okay.
All right. So a lot of chemicals in it. So one of the stories I tend to tell is about, early on in photography, the importance of gelatin. So gelatin comes from bones.
Bones?
Bones. Cow bones, pig bones. Shoulder bones.
Okay.
All right. And these are then digested. We're coming up on Thanksgiving. People are going to be making gravy, right? Got to, cook up your bones and get the collagen out of it. Collagen is on its way to the gelatin. So this is a bag of gelatin.
So film is organic.
Oh, well, yeah, absolutely.
So you said, question, you said that film is made of gelatin is made of bones.
And what the cows eat matter.
Really?
So early on, they found that a film got faster. And again, I'm going to say this story because it was been told to me.
Yeah, that's fine.
I wish I had firsthand proof that this is true.
Yeah.
But they found that the cows that they got the bones from had been eating mustard seeds and mustard grass.
Okay.
Very high in sulfur.
Okay.
It eventually started thinking about, sulfur is important.
Really? Kind
of started the Kodak research labs.
Interesting.
Because at that point, it says clearly there are ways to improve photography with different chemicals. Wow. And so now when I think about it, and when you talk about it, we may be putting in, counting really fast, 1, 2, 3, 9 to 12 different kinds of chemicals that improve the performance of silver halide.
Wow. Okay.
Some of that is dye, obviously, because we want a particular light, but we also want it to be a particular performance.
So do you purchase the gelatin?
Yes, we do.
Okay.
We have, I believe, 16 different kinds of gelatin that are used, some of them for coating, because we don't really care, because it's not really touching the silver halide grains that much. Some of them for the precipitation, and we really care. The molecular weight distribution of this definitely moves around, and we use those to our advantages. Different ion contents, some of them have magnesium, some of them don't. So we've learned a lot about the organic nature of gelatin and how it is plus and minus for performance of film.
Interesting.
We used to always say if there was a problem with the film, it was always the gelatin. It's not true, but it's a good scapegoat.
Got it. That's awesome. So this is melted down.
So this is dry.
Okay.
Water's added and it blooms. Anybody who's made gelatin, a little dry pack, and you put some water in, and it begins to bloom up. Right? Same thing.
Okay.
All right. And we'll talk a little bit about gelatin when we get upstairs.
Okay.
So where have I gotten us to?
So basically, this is what I understand so far. There's this material called silver halide, and it's got special structures on it, little planes where certain things happen. And if I hit it with a photon, my goal is to create silver atoms in one location.
A latent image.
A latent image in one location. You can control the size of the silver halide with the way you do the processing.
But the way we do the mixing.
The mixing,
right.
Okay? And then you can add certain things to it in order to enable the latent image to start in certain parts of the crystal.
That's a very good way to put it. I mean, it's more complicated, but that's a very good way to kind of say, how does an emulsion maker approach the problem of creating what's called a detector? We're essentially creating a photon detector.
And then once you do that, it's my understanding that you cleverly arrange these different layers of silver halide in the film, and you have different detector sensitivities, so to speak. And you've got the yellow, the magenta, and the cyan layers here. And they're sensitive to different colors of light, but essentially you stack them in different layers, and then the silver halide crystals are in gelatin as a way to hold it in a three-dimensional way.
A perfect lead into this picture.
Okay.
This is a sensitivity curve for blue light, green light, and red light.
Okay.
On your left-hand side at the bottom is no light, so there's no image.
Okay.
And at the right, there's a lot of light, and so there's a lot of density or image. Each of those layers that we looked at below, are the fast, the mid, and the slow.
Got it. So the slow layer on the bottom
are these parts here for the yellow, the magenta, and the cyan.
Yellow, magenta, and cyan. Okay.
Blue light, green light, red light.
Gotcha.
All right. And so this, we try to provide for the cinematographers or the photographers a very linear region here, because we want to, as the different exposures of a picture, we want it to grow correctly with the exposure.
Oh, so if you had like too much of the mid layer here,
there might be a bump here.
A step function in there, and that's bad.
That'd be bad.
So if I look at a sensitivity chart like this, a good one would look linear.
That's right. That's what we're aiming for.
Okay, that makes sense. And what are my units here?
Well, so this is density. So this would be reading out the coupler density, and we'll talk about couplers in a little bit. But the yellow dye that's in there, which absorbed the blue light. We're going to keep going back and forth with the material and the light. So this is yellow density, blue light, green density, magenta density, green light, and cyan density, red light. Okay. So these are the densities from a piece of film. It's not too easy to see this, but that increase of density, and it looks black, but what it is neutral. Okay. It's essentially this. Got it. So what you're looking at and this are the same thing. I see. There's no image, and the image slowly grows until it gets so high. But the cyan, magenta, and yellow dyes are all in that black.
So this is a test strip of sorts.
It's a test strip, exactly.
So you guys make these.
So after we're done coating a film, we'll slit it just like the perfed material out of the canister that you have. And we do that to do the test. Got it. That's amazing. That's cool. All right. So what I haven't done yet is talk about color. Okay. Talk about light, but that's not what you read out. Okay. So let me talk about dispersions and couplers. Okay. All right.
And this is the part that, admittedly, so I made a video on Smarter Every Day about how film works, and this was all fuzzy to me. This
Oh,
part, did I mess it up?
No, well, no, you did okay. It was actually quite good. I'm going to point you to another one that we made to talk about this, but it's perfectly good.
Okay,
right?
great.
So as a grain is developing in the photo processing, that means a developer molecule is diffusing through the film, comes down to a latent image, and donates its electrons to that piece of latent image silver. Those electrons then bring more silver ions to it, and you get this catalytic effect of the silver getting bigger and bigger and bigger.
Right.
In black and white, that'll ultimately be your image. You did an excellent job of the microscopy of the boy's eye, and going out and coming in. Very perfect.
Okay.
All right, for black and white.
Okay.
For color, the issue is that I need something that responds to that development. Well, the thing that responds to that development is the developer molecule becomes oxidized.
Okay.
Think of it now being incredibly active. It's able to do work.
Okay.
If we have a molecule that binds to the coupler, a coupler,
right,
that binds to the oxidized developer, and amazingly, that created color.
Right.
That's an image.
Got it. So the coupler, the act of using it creates color because you have a chemical in there that reacts.
Right, so it's colorless before the oxidized developer comes in.
Got it.
And it's colored after it reacts. So in the vicinity of the developing grain, there will be color generated with those that are put in the layer that we're looking at.
Okay.
Those are called dispersions. And they are basically, I always say they're like oil and vinegar. They're micellar structure. There's an aqueous phase and an oil phase. And the couplers are in the oil phase. And the aqueous phase have a surfactant, small little 0.1 to 0.2, very small micron. I don't want to say bubbles, but oil, salad dressing.
Right.
All right? And they are in that layer with the silver halide.
And you can pop them.
But yeah, let's call it pop them. When the oxidized developer molecule from the grain diffuses away, it will bump into one of these and create a colored image.
Okay.
If it diffuses too far, that's when you start having troubles that now I'm getting a dye, we call them dye clouds. They
little
amorphous,
blobs.
Yeah, blobs. If it goes too far away, it gets too big of a dye cloud. And that's the idea of possibly when we have really big grains, we have really big dye clouds.
Got it.
If we have small grains, we have tight dye clouds.
So the grains, though, the silver's still there, so you still have black.
Absolutely. So now I've developed up the film. I have black and I've got color.
Okay.
Now you do bleach fix actions, things that you talked about.
Okay.
We get rid of the silver.
That's what the bleach does.
Yeah.
Okay.
And bleach turns it back, fix takes it away, and you're left with just dye clouds in the film.
But that doesn't make sense to me, because if I'm taking a picture and I've got these colors right here, my color pictures still have black in them. So you still have to have some silver in there, don't you?
No. Your black comes from 3 color records.
You mix
So there is no silver in this.
Okay.
Only dye molecules. Only couplers.
Okay, so basically,
How you get black? Cyan, magenta, and yellow, all 3 of them right next to each other.
so it's not CMYK.
No. I mean, that's the big difference between inkjet, digital, and film, is we don't have K.
Got it. Okay, cool. So you're adding all 3 of these together and you get black. And
Right.
so my Ektachrome photo does not have silver in it.
Oh, neither does your, yes.
Neither does my C41.
Neither does your C41.
Okay.
To really take us away from silver halide, you ready to keep going?
Yeah.
Okay, so this building, we're in building 30 of Rochester Film Sensitizing, is where we make components.
Okay.
We have 1,200 components.
Okay.
All right, and components could be things we get from sensitized chemicals, very interesting couplers, dyes, all of that. We get 100 chemicals that just buy off the street. and then the other 800 we make here.
Okay.
We call them components.
Wow. Okay.
Components are
Chemical components.
Chemical components. And for example, an emulsion grain is a chemical component. Silver, halide, gelatin, water, surfactants, antifoamants, dyes, all of those things. So think of a imaging sensor as maybe having as many as, once it's sensitized, 20 to 25 chemicals.
Wow, okay.
So of those 1,200.
Cleverly arranged.
Cleverly arranged. You know, nothing leaves us unless it's perfect. But we need lots of chemicals. The film that I showed you here, this is a 500 speed motion picture tungsten balance film, has over 280 components.
Okay.
All right. So think back for a second. I just told you there's 20 to 25 chemicals per component, 280 components. And we'll talk about layers in a little bit.
Right.
So we're weighing out hundreds and hundreds of specialty quantities of material for each film that's going to be made.
Wow.
All right. That's where the other big magic is. And
the mixing.
Well, the other big issue is that when we get upstairs, you're going to see many, many vats of chemicals that people are going to be putting into various bottles and components, and they're going to go to different locations in the building to make those components. As well as some of these materials will be put to carts that will be taken across to building 38 to get ready for coating. There's chemicals for coating, there's chemicals for components.
Got it.
So I use the number about 700 weighouts, actively filling something like this precisely. And so what's big for us are barcoding.
Okay.
And we'll show that upstairs, but you got to track these hundreds and hundreds of weighouts for it to be exact.
Got it.
We miss one and we're wrong.
That's amazing.
Okay?
That's awesome.
All right. This is building 30.
Okay.
This section about making emulsions, making dispersions, making sure we got the right amount of weights of materials is what this facility is about.
Okay.
All right. Now we're going to start moving to coating.
Okay.
Okay? So once we have all those prepped, about 2 weeks before an event is coated, we say, hey, I need these components, I need these emulsions, I need these chemicals, and people start putting those in order. They're getting ready. And then they will be kitted together and moved across the bridge. You remember yesterday, we'll talk about the bridge again.
Yeah.
And they get ready for coating. All right? So what we have to do is to take bottles and containers of emulsion, which inside of this will look like a piece of Jell-O. It's about yay big.
Yeah.
And we got to melt that. All right? And on the wall there will be where we have batch melt. We'll go see batch melt.
Okay.
But huge kettles, maybe 10, 12 feet across, 4 feet high.
Wow.
Mixers where we begin to melt the gelatin and any other chemicals. It's very much a recipe. And they're dumped in there and they begin melting. There's another area which takes, I didn't really talk about this, but the chemicals that we put in together to get film to perform or the emulsions to perform are very temperature sensitive.
Okay.
We use temperature to aggregate molecules, to move those around on the surface to create...
It's your fine-tune adjustments of things.
Yeah. And if we do too much heat, it can go too far and an emulsion could be foggy.
Okay.
If we don't go far enough, it won't be sensitive enough. Some of those materials are highly sensitive to temperature. And so we'll put them on here, getting ready to coat.
Okay.
Right? And this is just we call it a passive liquid
So the
fire.
kettle sits on this?
No. Underneath would be the kettle.
Okay.
And we will put it on it, run hot water, and melt it slowly.
Oh.
Dripping it into a container that we will only pump out enough at a time to keep us going.
Okay.
So that we're not creating a huge kettle with hypersensitive materials where temperature will cause a problem.
Gotcha.
A coating event could be a couple of hours to as long as 8 or 9 hours.
Got it.
And if we have to stop for any reason in the thing, those are cooking away.
Got it. So that's gelatin, right?
That's gelatin, but other things can be in there. Emulsions could be in there too.
Okay.
All right.
I told you, he's a smart guy. It's amazing the depth that's there. Anyway, so now that we kind of have a grasp of what's going on with the film chemistry, we're now going to get to see how they do it. Like, how do they keep up with the chemicals? We're going to get to see the kettle that they actually mix the silver halide in. And for film photographers, this is like going to some sort of temple. Like, this is the actual kettle where the crystals get made in our film. So this is incredible, and I'm really excited to share this with you. So I hope you enjoy this part of the tour as well.
So we're not in operation Friday afternoon.
Okay.
So we might be walking into some various dark areas where I'll see if I can get the lights on.
Okay.
And I called my buddies to make sure certain things are turned on.
Okay.
But it's not going to look very busy.
Okay.
We're on the 8th floor of Building 30.
Okay.
And this floor is all around solution prep.
Okay.
All right, and in this big horseshoe are all our high volume chemicals.
Okay.
Acids, bases, surfactants, things we use a lot of quantity of, all right? And then on the other side of that horseshoe are kind of the next size of chemicals, things that are maybe a couple hundred milliliters, not gallons, all right?
Okay.
On the wall here is kind of a very efficient but looks outdated method of telling the operators what they have to make and get solutions ready for.
Okay.
So across the top is the 24-hour schedule. Down the side are the different activities. Make 610.
Okay.
That happens to be where we precipitate emulsions. But if they were going to make something Monday, it would probably start filling up here.
Okay.
Every chemical that they would need to do. So
really?
So what I'm going to see is an operator would come in and they'd say, I need to make up these solutions that are on these pages. And I don't want to get it goofed up, but they're all barcoded.
Uh-huh.
All right. They're all barcoded. So an operator would step up, grab the scanner, usually scan themselves to say who's doing the work.
Okay.
And then there's various scan positions on the paper, and it's say I'm going to be 10 bottles of surfactant. Okay. And they're going to scan the paperwork, enter in a few codes, hit run, and then this will fill up to the desired quantity. We put a label on it with the barcode set it aside. They'll get all 10. When they're all done, they shut this off.
So that barcode is now a totally different thing.
So the barcode that was on the paperwork is now charged to a barcode that says this quantity, which is, liter, is one of the 10 that you need for an operation, a precipitation, a coating event, a dispersion. This fulfills that order.
Where does it live now? Where do you take it?
Great. They're going to begin putting them on these racks around here.
Okay.
And a person's job is to make sure the right quantities, and if it's a huge, huge quantity, it won't go here.
Right.
It'll go to where I'll show you next. But these are then kitted up, and then a person's responsible for looking at what's needed and getting them all here and placed on a cart that's going to either go to like a making kettle, dispersion, or for a coating machine.
Okay.
All right. It's very tedious, but it's a way. So this is now the third time. Scan the wall, scan the site, scan the here. We're checking to make sure we've got the right stuff.
So it's the right mix of automation, but attention to detail and hand mixing the ingredients. It's the right mix.
Has to. So all these chemicals then are made in this mix station here. These movable materials are then rolled into position. A dry chemical would be put in there, the right amount of water. They'll mix it up, and then they'll load whatever chemical into these machines, these delivery systems.
And these light systems mean things to people.
Yeah, if it's flashing red, it says I'm nearly out. And they would have to take action, but green says it's ready to go.
Okay.
All right.
That's amazing. Okay.
So imagine that, again, back to our 1,200 components. That's one component.
Got it.
All right.
That's wild.
It's a lot.
It is a lot.
Let's see, what else on this floor? I don't want to short shift it because I actually, be good, Jeff.
You gotta put it back, Jeff. There you go.
Some inventory somewhere counted that, right? All right. Lots of components.
Yep.
All right. Let's go down to an emulsion making lab.
Oh yeah. Now we're talking.
All right. So this will be a dark hall if it's still dark.
Because we're on the emulsion layer. Do I need to?
No, you're good.
Cut the lights on.
No,
the camera?
we don't. Nothing's in operation today.
Okay.
I usually at this point make sure people's eyes have adjusted.
I'm good.
Before we start walking.
I am scotopic.
Excellent.
Okay, so we have shifted the cameras over. Trent's doing the same. So we've got the cameras at a really high ISO, but we can adjust and see a little bit. But everything's red, right, Jeff?
This is our safe light condition.
Okay.
We can precipitate silver halide in this light.
Really?
Because silver halide is only sensitive to ultraviolet and blue.
So we stay on the infrared side.
Well, yes, or red light, optical is just fine.
Okay.
We haven't added those chemicals that make it sensitive to the other spectra, okay?
I see.
So this is a pre-step in making the crystals.
And so it's interesting, the more we stay here, the more my light in my vision is adjusting.
Absolutely.
And I can't tell that it's red anymore.
That's exactly the way your eyes work. They adjust to the level of light and the color of light, and you can actually read fairly well, provided it's a little big type.
Yeah.
But this is the condition our operators work in when they're precipitating silver halide.
Okay, cool.
Now you gotta watch your eyes because I'm gonna turn lights on.
Okay, here we go.
Yeah, way to go, Jeff. There it is.
Woo! Okay.
So we've just moved to the light. This is not the condition that we'd be making in. This just shows all the different components, vessels that are used to create.
So this is silver over there now.
Yep. So this is silver nitrate, though, right? And the surface is hot because we're controlling the temperature. It could get as high as, I believe, 67 degrees Celsius.
Okay. Pretty toasty.
And we've precipitated down to 30, but that's pretty low.
Okay.
All right?
Wow. All right.
Silver, salt, so X.
Okay.
And then, GR is growth salt, and then auxiliary silver.
Why did you cover that? I didn't understand.
No, NR just means it could be sodium bromide, it could be
it's just something.
Potassium. NR is a reactor.
Got it.
Growth reactor is GR. Auxiliary silver, we might use two different sources of silver, one for growing the crystals, one for making the nuclei.
Right.
But yeah, different vessels that have different chemicals.
Got it.
All right?
Cool. So this is the kettle you're going to show me.
Yeah.
Oh, wow.
So inside there is a marine propeller on the back, kind of for bulk mixing, just turning
For
things.
agitator?
Yeah, once we're not precipitating, we might just move material around.
I see it.
But if you also see the baffles along the wall,
I do.
the mixing is a combination of, the pipa is a combination of mixing and pumping. And we want to get a good, we call it a roll, a good overall turnover of the volume of the kettle.
Okay.
We want to stir and we want to mix.
Okay.
Mix means those chemicals have to react together quickly and under control. Once they get thrown out into the wide outside, then we're stirring them around to come back. So this device that hooks to the pipa can be pulled up to the ceiling so we can, work on it.
Okay.
On this arm here.
Oh, I see.
All right. And all around here are various components that are going to get dumped in, gelatin and stuff like that.
Got it.
All right.
That's awesome.
So what has happened now? We add silver nitrate, we add some kind of halide, and I'm just going to call it sodium bromide.
Okay.
What do I have in the kettle? Microcrystals of silver halide. And now I got sodium atoms and nitrate molecules floating around. I got to get rid of them.
Okay.
If we were to dry this down, I would make these monster crystals of sodium nitrate.
That's not good.
Not good because it will plug things up, it'll scatter light. So we got to wash this somehow. So we're going to take a little trip, all right?
All right.
Follow the man with the light.
Sounds great.
We're going to go back to the bowels of the power supplies, the computers, and we're going to go see where we wash things.
Okay.
Kind of stay close. I'll point the light at you.
Okay.
Well, I don't think you need to. Wow, the lights are on. This is just, auxiliary areas for cleaning. There's power supplies. The kettle up there and the kettle up there are holding kettles for the two P231s. So after it's made, they get pumped to there. All right? And then it's going to go to a semi-permeable membrane tube wash. When this thing is running, there was nothing. These are louder than anything you heard yesterday.
Really?
All right. So the kettle is on the other side of that wall, and these 10 tubes have a semi-permeable membrane.
Is it a filter?
It's like a filter where it'll allow water and ions to go through, but gelatin and the silver halide crystals will not.
Okay.
We will wash out those ions until we get to a particular conductivity. It's because the sodium and this nitrate is going to make a conductive solution like a sodium chloride.
So you're using conductivity to measure your solution.
How clean the solution is.
Okay, got it.
All right, once we reach that, we'll then concentrate, because now we want to take out as much water as we want, because we want to set up the gelatin and store it in cold store. Okay?
Yeah.
So we wash and concentrate in this facility.
Serious pumps.
That's
right
some
here.
serious pumps. They're moving a very viscous material towards the end.
Really?
Initially, it's kind of like very much water.
So it's like peanut butter.
Not that far,
Okay.
but it's on its way.
Okay.
Yeah, that's a good analogy, but it's not quite that far.
Okay.
All right, take a left.
Take a left. You have this place memorized, don't you?
Not nearly as well as I should. I can get lost very easily. Brian, yesterday, I could have never taken you quickly through those different spots.
That's amazing.
All right, now it's a question of what you want to see.
Gelatin.
Very good.
Okay. Is that cool?
Yeah.
All of this is cool.
Yeah. We're in the bowels.
This whole room are different flavors of gelatin.
Really?
Not flavors in the raspberry orange kind, but
So this is the Willy Wonka room.
so in this room are where we inventory our gelatins and get them ready for delivery.
Okay.
Those kind of funnels there are for easy of us to load a usable supply.
Got it.
Here's
That's a Gaylord, right?
yeah.
So this is the gelatin.
This happens to be the coating gelatin. So we have emulsion gelatin. We have different gelatins that respond to pH differently. I'll tell you about that.
Okay.
But this is the bulk gelatin that's used for coating.
Got it. Awesome.
So I told you there's 127 emulsions.
Yeah.
We make 71 different films. So those different businesses, I don't know if I told you that number.
Okay.
And we have about 60 some dispersions. Dispersions that create color. Cyan, magenta, and yellow. And dispersions that create active chemistry. That's very complicated, but I might want sharper colors. So when cyan is being imaged, I don't want magenta and yellow going off. So we actually send chemistry up, I say up from the bottom of the pack,
Right.
to shut down any grains that are developing above it.
Wow.
So as there's a big signal of red, we're going to try to influence the other layers.
Shut off the yellow.
Yeah, and they turn on at a time clock so many milliseconds after so they don't shut down the red layer.
Wow. That's crazy. And this is all chemical.
It's all chemical.
That's crazy.
And then there are ones that we want to, if we have a big grain, we really don't want that thing to develop fully, because then you'll have a really big dye cloud and it'll look granular and you'll see it. So after some grains start developing, we have dispersions that are called inhibitors.
Right.
That will shut the development of the silver down. We'll try to slow it down so that other grains will take over.
Yeah.
Right?
Yeah. Matt's shooting with a Hasselblad like a boss. So cool. So cool. If you want me to shoot any of you, let me know.
I would appreciate it.
This is why it's a little boring on Fridays. All the chemicals that need to go across the bridge would be lined up here by each film code.
Gotcha.
All right, so 1903 is a printed circuit board film. Monday morning, this will be loaded up. All right, and this is another PCB, another one. On Monday to Tuesday, they're loading stuff up to transfer over.
Awesome.
All right, but you kind of see what they'll look like. They'll kind of look like this.
So this is one big mixture for one big cart.
Somebody might be taking some of these to fill, or these carts can be ready to go. All right.
That's awesome. It's like a recipe.
Absolutely. These two elevators bring up stuff from the cold storages, so the emulsions and dispersions in those black containers.
Right. The black containers because they're light sensitive.
Yeah.
This is the bridge.
This is the bridge. We're back. Did I show you this?
You didn't tell me what it was.
So this is the start, and this is by the end of this production line, we stop having humans touch stuff.
Really?
That's an important part of our quality. All right. So those carts come in here. All right. An operator is going to take, in this case, a 4-gallon jar that would be on the cart. He's going to marry the barcode to the chemical. And now this becomes the chemical. Loads it at it.
Does he take the top off?
Nope. We have robots that do that.
Okay. Wow. Really?
I'll see if I can get in there, okay?
Wow.
But this starts going. And this will be running continuously till all the chemicals that are needed in building 38 have been moved from 30 to 38.
Awesome.
When we were 24/7, this thing never stopped.
It's amazing.
All right, so now as this goes around, the barcode here will be scanned automatically and it'll be diverted or go to wherever it needs to go.
It's amazing, yeah. So you have a pretty good maintenance crew here.
Very good, very talented. This is the last stop before 38, and if the weight does not match its design parameter, it gets kicked off. And somebody's got to figure out something. If everything's good, it comes in, and on this side, we're feeding the machine.
So this is all chemical handling.
Material handling.
Okay.
Right? On this side, we're feeding the machines. We're going to feed those elevators. And on the back side, empty cans are coming, containers are coming back. And that is a queue section that goes, I mean, we got Disney World beat here. It can be just loaded with storage. We just don't have as much volume right now. But that would normally be full of empty cans.
That's awesome.
Some of this should look familiar.
It does.
We were here yesterday. The elevators over there bring the material down that are going to go into batch melt. And they will load onto specific carts that will be a cart per melt.
Okay.
All right? Then we'll go back.
Okay.
All right.
So the chemicals come in on our cart, and then it's time to put them in a, what we're going to call it, the melt?
What we're going to add a melt. So we'll take this cart into the room.
Okay. This is the dark room.
Batch melt.
Batch melt. And some of those chemicals were light sensitive in the black bottles.
But there will be an operator up on this platform.
Okay.
And a cart will go in here.
Operator on platform, cart goes in here.
And the cart will be raised up so the operator can then pull those black containers off.
So step up here. So we brought our chemicals in here, and the operator will receive it right here,
and the operator will put it in this device here, and this device robotically dumps it. Interesting.
Right.
Okay.
So these are all those square-topped black containers.
Gotcha. Okay. That makes sense. This is a lot of automation for pouring fluids in vats.
So nothing's a fluid, solids here.
Oh, okay.
Chilled gelatin containing silver halide or dispersions.
Understood.
Solutions would be dumped in by a bottle.
Understood.
But just to give you again the size of this room, it just keeps going.
Yeah. Okay, so I'm gonna come over here. There we go. I figured my camera
and
out.
if I just tell you something, an example here, 214A, that thing here, and 214B,
Yeah.
we could bring in 2 kettles here and here, drain one, shift to the other one on the fly, bring in another one if we have to, if the volume of the needed melt is high.
Right. So how long does it take to get a melt going?
A couple of hours.
So we're on
2.5 hours, depending on the gelatin content. Too much gelatin and it's like a rock. And it takes a while to get it melting.
Okay. So that's a boat motor right there, isn't it?
And the thing that I'm not able to show you, I hope I'll see one, is there are all kinds of jacks that feed into the wall, both for water supply to take care of the jacket, as well as to deliver things down through the bottom and into the automated delivery system.
Wow, this room is big.
Yeah. Here we go.
Nice.
So all of those, you know, certainly the ones at the bottom are feeding materials in, but water supply, mixing, locking it in place, those kinds of just plugging it into the wall.
So that makes water flow along the inner wall.
The jacket, right.
Yeah.
And then the others deliver the contents downstairs, which we may go to next. That's the advanced delivery system, or automated delivery system.
Man, I can imagine this is very difficult for maintenance people because they're working in the dark.
Yeah, and you know, it depends. If the maintenance is such that it shut us down, we'll pull the materials back, store them if we can, do our work, and come back.
Wow.
All right. This is ADS.
Okay.
Automated or Advanced Delivery System.
Okay.
Okay. And
So this is after we've melted the melts.
right. So we're one floor lower. We were up a floor, and melts will come through the wall, not through the wall, but through pipes.
Yep. I'm seeing a lot of filters here.
You are.
Okay. This is an
Each-
incredible amount of piping.
Yeah. So each of these is a system where above, and this happens to be FAM, we haven't gone there, but it's the advanced melts are dumped onto those coils, and that's where they are, is right here.
Right.
And they drip into a sump, and they're delivered to this side.
Wow.
And we'll, hopefully I can find a light in here.
How much did this facility cost?
Over $1 billion, 1.3, I believe.
Billion with a B.
Yeah. So this room is where every one of those kettles upstairs come into eventually before they go up to the coating machine.
Okay.
And the reason why it says keep out, it's hot, is we're trying to keep everything the same temperature.
I see.
And it's hot.
And it's hot. Okay.
This
Oh, it
isn't-
is hot.
This isn't hot.
This is not hot.
This is Friday. No, it's warm. But if you start counting, all of these are each micro motion detectors, or two.
Like a rotometer? Like a flow meter?
It's a flow meter.
Yeah.
Yeah. But we're delivering this up, and if you recognize the geometry, one side went to one coater, the other side went to the other coater.
Oh, so we're under the coating.
We're very close to coater. I'll take you out and show you that. But I didn't point it out when we were upstairs. Right on the back side of those mix boxes was like all these pipes coming up.
Right.
So we want the thermal stability so that when it's delivered up to the coating hopper, there is no thermal currents that would set up an eddy, you know, and we want that laminar flow.
Okay.
And you know, that titanium container, that hopper up there is trying to maintain its dimensional stability.
Okay.
So we don't want to send cold water or there even to be any difference from top slot to the bottom.
So we have a thermodynamic issue.
Yes.
We have a mechanical issue.
Yes.
We've got fluid dynamics. We have photochemistry.
Yeah.
We have almost everything.
Yeah, we'll even add some more as we go.
Okay, that's incredible.
Everything matters. All right. So we got to get out of here because it's hot.
It's very hot.
So I've taken several runs at the outro to this video because it's an incredible video. Like, there's an amazing amount of information that Jeff just gave us. And this is unique to the internet. Like, it's rare to have such an important piece of documented industrial history on the internet. This is incredible. And a couple of things I want to say is that, number one, Jeff is a unique person. He's very humble, he's very knowledgeable, but Jeff is aware that there's so many other people there at Kodak, and he was sensitive to that. He wanted, a couple times he was like, hey man, there's a lot of people that do this, and I should have got this person on screen, I should have got this person on screen. I said, Jeff, you were the person that was available today, and we made an amazing video, and I will make sure to say that you are thankful and aware of all the other people that work with you on a team, because Jeff is a team player. You can see him mentoring other people. In fact, I asked him about the future of Kodak, and he said they're already trying to figure out replacements for different people in different areas when the other people retire. So I was just impressed with the work atmosphere. It felt like family, and I really enjoyed it. Yeah, so I don't know if that encompasses everything I wanted to say, but I think you can read my heart. You understand what I'm trying to say, and I'm grateful for that. Also, there's another video about how they check for quality. They check the film. They actually process it, and they do what's called the sensitometry, and they measure that, and they see if everything is where they want it to be. So on the second channel here, there's another video to watch that's equally as interesting. So if you're into the depths of how film works, please go consider watching that video. And of course, there's the main channel video about how they actually weave the film through the plant. So all that to say, I want to say one thing in particular. Thank you to the patrons of Smarter Every Day. If you don't know, there's this group of people that support Smarter Every Day on Patreon. It's patreon.com/smartereveryday, and they let me make the videos I want to make, because the algorithm doesn't always reward extremely in-depth thing on one particular topic that I'm interested in. And so the thing that Patreon does is it lets me make whatever I want to make. Kodak did not sponsor this video. They gave me access, for which I am very grateful, but it was a pretty big outlay to go make this video and spend this time with animations and editing and all this kind of stuff. So I'm grateful to the patrons of Smarter Every Day. If you would like to consider supporting on Patreon, and when you do that, it's like you kind of helped make the video. There's this goodwill thing that happens, and I don't know, people that support on Patreon know that they kind of own a little portion of this video because they helped make it. So if you're interested in that, I send everybody a baseball, patreon.com/smartereveryday. I'll send you a baseball, and every once in a while I'll send other stuff as well. I try to under-promise and over-deliver. I hope you get out there and take some film photos now that you understand the chemistry of what you're doing, and I hope you're as excited about that as I am. And with that, I will just say thank you for watching these videos. I am Destin. You're getting smarter every day. Have a good one. Bye.